How is everybody? Got a thumbs up from Ronnie. Thank you. Got a thumbs up from Edwin. Thank you. Okay, we are at day 20. Can you believe it? Can you believe it? So, any questions before we get going? You've got that special homework that's due on Wednesday. There was an incredibly productive office hour last night. The video is up. I have elected not to post the office hour notes because there are some complete solutions included in those notes. And I really want folks to listen to the video rather than just copy down a solution. But you will find numerous um, big helps with that homework in that office hour from last night. So I just wanted to let you know. You may not have had a chance to look at that yet, but you don't want to wait too much longer. All right. Any questions? All right. So I'm going to pin our notes. Um, that's our commercial for our office hour. So our goals today are to talk about recursively defined sequences. We're going to talk about a famous one, and I bet you even know the name of it. Once you see it, you'll probably recognize it. And that's section 5.6. That WebAssign is already posted and is due Thursday. So it's not that many problems on 5.6. Then we'll cover 6.1, and that WebAssign is due Sunday night. You know, it's always 11:59, unless it's right before a test. So you'll have a little more time for this one. And tonight we're going to review set operations. It's been so long since we've talked about sets, right? It was way back in section 1.2, like the first and second days of class. So we're going to review set operations, the union, the intersection, and the set difference. And then we're going to look at some Venn diagrams just for fun. Those won't be on the test, but they're very helpful in understanding set operations. We're going to talk about the universal set and the set complement, which is another set operator. The cross product. I think we covered the cross product, but we're certainly going to recover that tonight. And this will all help you with your WebAssign and your next special homework number 10 that I'm still working on, just putting the last finishing touches on that. It will be due Monday. Of course, that gives you all weekend. We're going to review subset of and proper subset of. I don't think we've discussed proper subset of, but it's a very natural concept. It's kind of like the difference between less than or equal to and strictly less than. And we'll even see that reflected in the notation. And then we're going to review interval notation. And on Wednesday, we're going to pick back up with interval notation and talk about partitions and some interesting problems involving interval notation. So this is a really useful notation. So to motivate tonight's lecture in 5.6 on recursively defined sequences, I've laid out what is the definition of actually a recursively defined sequence. And I just want to see what you can do with that. Now, this has been up for a few minutes and folks have been in the room, so maybe you've already taken a look at it. Recursively defined sequences, folks, have two parts, and you're seeing that reflected here. The first part gives us the actual values of some initial terms. And interestingly enough, it's sort of like induction. This is called the basis of the recursive definition. It sort of tells us where we get started. And then there's another part of the definition that's called the recurrence relation. And it tells us what is the essential nature of the sequence. And all recursively defined sequences have something in common. To look forward, we look backwards. So to figure out what A sub k is, folks, we have a formula that involves the prior term, A sub k minus 1. Notice this formula also involves the integer k, and this starts with k greater than or equal to 2. Your recurrence relation always starts at the integer that is just above where your basis left off. So here our basis was about A1, so our recurrence relation tells us how to define A2 when k is 2, or A3, A4, and, forever after. So can you find the terms A1, A2, A3, and A4 with this recursive sequence? Let's do that together. Of course, A1 is easy because it's given to us, right? So when K is 1, we're told that A1 is 5, right? So it's never a problem to find the first few terms because they're given to us. Sometimes the recurrence relation will be a function of several terms behind. This is just the single term a sub k minus 1 in that definition, but we'll see some more other examples where sometimes we have to look at 2 prior terms or even more. All right, so when k is 2, we start using the recurrence relation because it starts for k equals 2. Did anybody find a value for A2 during this period of time?
I got 14.
Anybody else get 14? I think that's right. Let's take a look. So a sub 2 means, okay, k is 2. Everywhere we see k, which is as the coefficient in this expression for a sub k minus 1, we write 2. So k is 2 times a sub 2 minus 1. So this is, again, arithmetic inside the indexing numbers. We're actually going to figure out what a sub 2 minus 1 is. Of course, that's going to be the prior term. It'll be a sub 1. But the formula also says, go ahead and add k squared, which of course is 2 squared when k is 2. So we're looking for 2 times a sub 1, because 2 minus 1, of course, is 1, plus 4. And let's see, 2 times a sub 1, well, a sub 1 was given to us, it's 5, plus 4 is certainly 14. Good. Everybody see that? Any questions? All right, so everybody go ahead then and find k equals 3, a sub 3, and see if you can find a sub 4 as well. If you don't have any questions, I'm assuming you understand. So I'll do it here. When k is 3, we're going to put 3 in there, and it'll be a sub 3 minus 1, right? Plus 3 squared. So it's, oops, gotta find my whiteout. Can't live without my whiteout. Oh. Here we go. This should be equal to. What are you getting for a sub 3, folks?
51.
Hey, I think that sounds right. Anybody else getting 51? It's 3 times a sub 2, right? Plus 9. Well, we found a sub 2. It was 14, so it's 3 times 14. Plus 9. And that's 42 plus 9. I'm getting 51. Is that what you'd said? 51?
Yeah.
Perfect. Everybody see how the game works? What about a sub 4? Has anybody cranked out a sub 4 yet?
220.
That sounds right. Anybody else getting 220?
I got that too.
Awesome. So it's 4 times. Do we even need to write 4 minus 1 here, or does everybody realize it's a sub 3? Sometimes you can just go to, you don't have to show this work. I'm showing it for the purposes of the notes. But, once you get the drift, right, then you understand, oh, k minus 1 is the term right before a sub k, right? A sub k minus 1. So it's 4 times 51 plus 16, and 4 times 50 is 200. 4 times 1 is 4, so 204. But yep, I'm getting 220 as well. So it's a fun game. Nothing, up either sleeve here. This isn't hard stuff. It's just kind of fun. And I think that you'll find this next homework after working so hard on induction proofs. I think you'll find the homework number 10 a little bit delightful because it's not going to be so proof heavy. So there are a couple of facts. Do you remember when we talked about geometric and arithmetic sequences? Remember, a geometric sequence is a sequence that you get by having an initial term and then multiplying that term by some common ratio to get the next term. And then we multiply that term by that same common ratio R to get the next term. And we just keep multiplying by R over and over and over and over to get the subsequent terms. Well, here's a fact. Fact number 1 that you will enjoy. Every geometric sequence can be, doesn't have to be, but it can be recursively defined. And why is that? Well, just imagine we're given some initial term, some, starting term, that's our basis, but we've called it the initial term. Usually it's, subscripted with 0, right? And then we're given a recurrence relation. And I do believe that we even heard that phrase, recurrence relation, before, where we get a sub k by taking R and multiplying it times the prior term, a sub k minus 1. And that would start at 1 and for every k bigger than 1. So every geometric sequence can be recursively defined. That's our first fact, trying to tie in with things that we've seen before. But the second fact is not going to be a big surprise either. Do you remember arithmetic sequences? Does anybody remember? And I know you've had WebAssign on these. Does anybody remember what it is that happens between the terms in an arithmetic sequence? What do we do over and over to get subsequent terms? Do you remember? That's when we add something. That's called the common difference. Sound familiar? Okay, so every arithmetic sequence can be recursively defined. So it's a very kind of symmetrical idea here. In the same spirit as the geometric sequence, with the arithmetic sequence, we are given an initial term, and it's often indexed with a 0. I'll call it b sub 0 just for a little bit of variety here. And then the recurrence relation is adding the common difference to a term to get the next term. So b sub k is equal to the term b sub k minus 1. I almost made that an a. See that? Plus that common difference that we usually call d. And remember how we got the common difference. If we subtract b sub k minus 1 from both sides of this equation, it shows the difference between b sub k and the prior term, b sub k minus 1, is d. And that happens over and over and over again in an arithmetic sequence. It's always going to be the same common difference. And in fact, that's one of the ways we can figure out if a sequence is arithmetic or geometric. We can check a term minus the prior term and see if we always get that same common difference. All right, so let's look at another example because I want to show you that it's not always just one prior term that would define subsequent terms. Let's let the sequence, and here I'll reintroduce some notation that we've seen before. We'll say E sub I, so this denotes a sequence, and it tells us we're going to be using the letter E for the terms, be defined as follows. Well, E sub 0 or E naught is going to equal 2. E1 is equal to 3. And our recurrence relation says E sub k is E sub k minus 1 plus 2 times E sub k minus 2. And this starts happening for k greater than or equal to, well, you tell me, what would be a reasonable place to let our value for k start if we're told what E naught is and what E1 is? Check in the chat to see if anybody's chatting in.
Two?
Yeah, because we know what E sub k is when k is 0, and we're told what E sub k is when k is 1. So this better start with k equals 2 and keep on working. So again, folks, we have a basis or an initial term, and then we have a recurrence relation that gives us the relationship between prior terms and subsequent terms. I like that word, subsequent. So, I mean, what's a reasonable question here? Find the terms, let's say E naught through E5. Okay, so let's do that. Well, E naught is given to us, right? So when k is 0, we're told E sub 0 is 2. That's given. So we can just write that down. And in fact, it's true for k equals 1 as well. We're told E1 is just 3. You see, when the recurrence relation depends on 2 prior terms, then we have to be given 2 terms to initialize the whole definition. Does that make sense? Okay, I'll take that for a yes. So can you find E2, folks?
7.
Okay, let's check that. So it's when k is 2, we start using the recurrence relation, and it says E sub 2, when k is 2, is equal to E sub 2 minus 1 plus 2 times E sub 2 minus 2. So, of course, that's E1 plus 2 times E naught. And that is 3 plus 2 times 2. Yep, 7 looks good to me. So go ahead now, folks, and just get a little practice in and find E3, E4, and E5. And then I'll work on them here, and you work on them there, and you can check in as you need to. What are y'all getting for E3?
9?
Okay,
I got 13.
let's see. I've got, it's E sub 2, right? Plus 2 times E sub 1. Is that what you're getting? E sub 2 plus 2 times E sub 1? And E sub 2 is 7. And 2 times, well, E sub 1 is 3, so 2 times 3. Yeah, I'm getting 13 as well. Edwin, do you know?
Yeah, I forgot to multiply the 1 or E sub K2 with 2.
Uh-huh.
Make
Okay,
it
good.
6, and then 6 plus 7 is 13.
Okay, that makes sense. Right, our coefficients made a difference here. Okay, cool. What are y'all getting for the E4?
27.
Anybody else getting 27? E3 plus 2 times E2. Let's see, E3, 13 plus 2 times 7. Yeah, 13 plus 14. Yep, I'm getting 27. Cool. And let's just do one more for good practice. I think these are just sort of relaxing, to be honest. plus 2 times 13 equals, are you getting 53, anybody?
Yeah.
So I have a question for you. As you look at this sequence, starting with E1, it doesn't hold for E0, but if you look at this sequence starting with E1, do you see any kind of pattern going on? Thanks, Ronnie. Yeah, I've got your chat open. I'm going to take my glasses off so I can read it. Anybody see a pattern here?
It goes like it doubles and then minus is one, and then it doubles again and it's an add one, and then double again, minus one. I don't know if that's a good pattern.
Yeah, yes. Yeah, first it doubles and you subtract one. Well, first we double 3 and add 1, get 7. Then we double 7 and subtract 1 and get 13. Ooh, I like it. Then we double 13 and add 1. Then we double 27 and subtract 1. That, you know what? I did not even see that pattern until you pointed it out. I think that's happening. I noticed a different pattern. Does anybody else notice sort of just like that? That was pretty deep what you just figured out. Does anybody notice kind of a simpler thing going on just looking at the numbers themselves?
Alternates between 3 and 7 on the second part of the number.
That's right. This is called the second part of the number is called the ones digit. Yeah, it alternates from 3 to 7 to 3 to 7 to 3, and then the next one is 7. I've checked it. So if we have these conjectures, do you have any idea how we might prove any of them? We have a proof method that would lend itself to proving that a sub k plus 1 is either 2 times a sub k plus 1 or 2 times a sub k minus 1. We have that conjecture, and the other conjecture is that the ones digit is for a sub k, starting with k equal to 1, is always going to be 3 or 7. That would be a proof by induction, right? So if you want to try to prove one of these two conjectures by proof by induction and turn that into me, that could earn you 10 extra credit points on your homework and quiz score. We can also discuss during office hours. I think that would be fun to try to prove either one of those. And I've never proven either one of those. So I think that might be fun. Speaking of fun, let me give you a little history. Did you know that in the 1800s, late 1700s, and early 1800s, the algebra expressions that mathematicians wrote differed depending upon where they were in the world? There wasn't even a standard algebra. What that means is, just imagine this. It's hard enough when we, agree on what algebra means. But if two different mathematicians are trying to communicate mathematical ideas and they don't even use the same notation, one mathematician could write an expression that the other mathematician literally would misinterpret simply because of the notational differences. One of the ways that mathematicians got around this problem is that they would write mathematical problems in prose, as stories in paragraph form. And as kind of an interesting sort of historical note, I want to try to give you sort of the modern English version of the letter that a mathematician wrote to his mathematician friends describing a problem, a mathematical problem. And it's about rabbits. So I've called it A Rabbit's Tale, and that's tongue in cheek, of course. So here's the way the story goes. And remember this. One of the things that mathematicians are allowed to do when we're trying to figure out something fairly difficult is look at the simpler examples and see if we can learn anything or prove anything just about the simplest kind of scenario. So it's sort of like a toy problem. So you can view that like this, as a toy problem. So a pair of rabbits. Okay, so what do we have? Folks, we've got one male and one female are newborn. Okay, so you're gifted. Just imagine somebody hands you this newborn pair of rabbits. After 2 months, They are in the adult phase, so they've grown up. And can reproduce. All right, but here's where sort of the toyness comes into this problem. So here's how they reproduce. At 2 months of age, they have one pair of baby rabbits. One male, one female. So definitely not realistic, but still fun. Every month. So starting at 2 months, they have one pair of rabbits every month. One male, one female. And the same rules or the same rule of reproduction applies to all offspring. So once they get to be 2 months old, they have one pair of baby rabbits every month, one male, one female. So, so this is an incestuous tale. Rabbits mate with their twin. And that's the only rabbit that they mate with. They just mate with their twin over and over again. How many pairs of rabbits are there? At month N? So it's definitely a math problem, but it turns out to be kind of interesting because it turns out to be a recurrence relation or a recursively defined situation. All right, so does everybody understand the rules of reproduction? So let's look at the rabbit's tail in pictures. All right, so over here, we're going to have the month. And then we'll draw the picture sort of in the middle. And over here on the right will be the number of pairs. So we're going to just see what happens with this value, the number of pairs. Okay, so at month N equals 0, the rabbits are newborn. So I'm going to draw them small, just 2 little baby rabbits, one male, one female. Okay, they're brand new. Now, at month N equals 1, well, they're now teenagers, they're adolescents, so I'll draw them kind of skinny but taller. But they're still not old enough to have any rabbits themselves. So at month N equals 0, we have one pair. At month N equal 1, we still have one pair. Bet you were wondering when I would start filling that in. All right, let's take a look and see how many pairs we have at month N equal 2. Well, the adolescent rabbits have now grown up into full-grown rabbits. I'll make them kind of grown-up looking. And now they've had their first pair of babies because they're old enough. So we have 2 pairs of rabbits. Everybody with me? How many pairs are there at N equals 3, folks?
3 pairs.
There are. How'd you get 3 pairs? We have these grown-ups.
Grown-ups like reproduce. They produce another set of pairs, and the other pairs grow up into adolescents.
That's exactly right. So these grown-ups get to have another pair because that's what they do every month like clockwork. And the adolescents are now what used to be the babies. So these are a little bigger, but still not old enough to reproduce. So we have 3 pairs. How about after or at, N equals 4? Let's see. What do you think?
5.
I think that's right, because now these adolescents, I gotta draw them a little fatter because they're grown-ups now, aren't they? And they have just had their first pair of babies. So the original bunny rabbits are now grand rabbits, right? And their second pair is now, well, those are adolescents, but still not quite old enough to get to it, but they have a third pair of babies. And that is 5. Yep, that's 5. Everybody with us? So what about at n equals 5? Well,
8.
I think that's right. Let's just double check. The originals have this first pair of adults now who are having their second pair of babies, and their first pair of babies are adolescents, so not old enough, but this second pair of bunny rabbits are now adults, because they're 2 months old now, and so they get to have their first pair of babies. And this third pair of babies are adolescents, so they're around, but they're not old enough yet. And then, of course, the originals are still at it, right? And they've had now 1, 2, this is their fourth set. So yeah, so 1, 2, 3, 4, 5, 6, 7, 8. That's exactly right. Now we can play this game ad infinitum, but let's just take a look at the sequence that we got. 1, 1, 2, 3, 5, 8. So the sequence, which is defined to be the number of pairs of rabbits, is like this: 1, 1, then 2, 3, 5, 8. Anybody recognize the sequence?
The Fibonacci sequence.
It is. It's the Fibonacci sequence, and the mathematician that wrote this letter was Fibonacci. So, do you know the rule? Do you know what the next term would be?
13,
It is. How did you get 13?
because you add the term previous to it.
Plus
Okay.
the term before that, right? That's
Yeah.
exactly right. We add these two, the term previous plus the one before that. And so that makes the next term of this sequence 21, right? And you can keep going, right? So this is called the Fibonacci sequence. Indeed, indeed. And it has a recursive definition where, eventually to get a term, you just add the two prior terms. See, 2 is 1 plus 1. 3 is 2 plus 1. 5 is 3 plus 2, and so on and so forth. That's exactly right. So let's write the actual definition of the Fibonacci sequence. Let's write it. Fibonacci. Anybody know what nationality Fibonacci was? Can you tell from his name? Like Da Vinci, Medici. Yep, that's right, Ronnie, Italian. So, by the way, the letter we use is F for obvious reasons. We usually even capitalize it. Now, some authors don't bother to capitalize it. Sometimes you'll see a lowercase f, but F naught is 1. F1 is 1, so we're indexing with the month. And then F sub k is equal to F sub k minus 1 plus F sub k minus 2 for k greater than or equal to 2. So I'd like to give you another do now to help you with one of the WebAssign problems which is an interesting identity that's true for the Fibonacci sequence. You get to prove an interesting identity. You get lots of help, though. It's a bunch of pull-down windows, so it's not too bad. But this should help you with that. Find an expression for each of the terms. In fact, they are Fibonacci terms. So let's go ahead and say that. Each of the Fibonacci terms listed below, where K is as indicated. Usually, I think in WebAssign, the author just says, hey, just let K be a reasonable K for which this is defined. But here we go. For the first one, can you write an expression for F sub K plus 2? This will be for K greater than or equal to 0, because I want you to understand that we are not going to allow this index number to be below 2 because the recurrence relation starts for K equals 2. So when I say write an expression, just understand we picked K so that the recurrence relation is what is in play here. It's just a game with indexing numbers. All right, and then for B, write an expression for F sub K minus 1. That'll work for K greater than or equal to 3. And the last one that we'll do is F sub K plus 4. That'll actually work for K greater than or equal to negative 2. So do you understand what I'm asking for here? All right, let's work on this first one together. The point is, when K is 0 or bigger, then K plus 2 is 2 or bigger, and that means the recurrence relation is the part of the definition that applies. So in other words, we're just going to practice writing the sum of the two prior terms when the original indexing number is K plus 2. So this will be F sub K plus 2 minus 1, inside the indexing number, plus F sub K plus 2 minus 2. Does that make sense? And doesn't it make sense if we look at the number line, right? The two integers that are before K plus 2, like if we drew a number line, right? If this is K plus 2, then the integer before that would be 1 less than that, which is K plus 1. And the integer before that would be 1 less than that, and that would be K. So you can always draw a number line. So this is F sub K plus 1 plus F sub K. Okay. So if you didn't quite understand what I was asking for, I'm just asking you to try to write each of these as the sum of the two prior terms, doing the work inside the indexing variables. Okay, so you work on those two, and I will work on these two. What are you getting for B? This is hard to chat in.
F
Usually,
of
go
K
ahead.
minus 2 plus F of K minus 3.
Yeah, F sub K minus 2 plus F sub K minus 3. And that makes sense, because if you keep going down, 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 the one to the left of K would be K minus 1, and then K minus 2, and K minus 3. Wait a second, this is a 3. Okay, just want to make sure it looks like a 3. Well, it was better before. Good grief. All right, what about this last one? What are you getting for it?
f of k sub 3, or f of k plus 3, sub k plus 3 plus f of k sub, or f sub k plus 2.
Nice job. That's a mouthful. Everybody okay with this? Okay, great. There is one other little proof problem in the 5-6 homework. So I want to do one that's similar. Consider this geometric sequence, and it's going back to the idea that geometric sequences can be recursively defined. You don't have to believe me. Let's look at an example and convince you. All right, so this sequence is that b sub k is equal to 3 raised to the k for k greater than or equal to 0. Folks, this is called the formula. This is an actual formula. Remember, we worked on general formulas for sequences and general formulas for summations. This is the general formula, and this is what we're given. So it doesn't hurt to put a little box around that just to kind of recognize, hey, this is what we're given as our hypothesis. It's given. And what we're asked to prove is to show that the sequence b sub k satisfies the recurrence relation, or this recurrence relation. I'm going to give you a recurrence relation. For k greater than or equal to 1. And the recurrence relation that we want to show that is satisfied is this, that b sub k is equal to 3 times b sub k minus 1. I mean, we're multiplying by 3 over and over and over again. So this is what we wish to show. I'll put my little dreamy wish cloud around that. So we can prove this by just noticing a couple of simple things. This formula works for any value of k greater than or equal to 0. And certainly a value when k is greater than or equal to 1 means b sub 1 is going to be defined according to the formula. And b sub k minus 1, well, that's at least b sub 0. K minus 1 is 0. So it'll still be defined by this formula. So notice, for k greater than or equal to 1, the given formula tells us this, that b sub k is equal to 3 raised to the k, and b sub k minus 1 is equal to 3 raised to the k minus 1. Why did I look at these two expressions? Because these two expressions are involved in the equation that we wish to establish, right? If we're going to establish that this equation is true, we need to know what b sub k looks like, and we do. And we'll need to know what b sub k minus 1 looks like. Oh, we do, because we're given a formula. So finally, we can just verify that this equation holds by noticing that, hey, b sub k is 3 raised to the k, but that's 3 times 3 raised to the k minus 1, which is 3 times b sub k minus 1 by the definition. So this is just a little example to show you how simple it is to show that a geometric sequence, which always has this general form. If you go back and look at the notes for geometric sequences, it's r raised to the k, where r is the common ratio, will always satisfy a recurrence relation that looks something like this. You just multiply by that common ratio r to get the next term. Questions? Okay, I think that covers what I wanted to say about section 5.6. Of course, always, folks, I encourage you to read the book. Reading the book is always a good practice, right? So, set theory, let's do some review. We are now in section 6.1. Okay, we've just moved out of 5.6 into 6.1. So let's recall the following definitions. Given sets A and B. All right, the first definition is the definition of union. So the notation is A with a cupped up U, no ears, B. We read this A union B. By the way, you can relate set theory notation to statement notation. The union symbol, which looks like a U, which has helpful, also looks a lot like the OR symbol, which was pointy, right? The V. And this is the OR operator for sets. In other words, the elements that are in A union B are X, such that X is an element of A, or X is an element of B, or both, because we use the inclusive OR in our logic. So that's the union. Elements that are in A or B or both. Now, what about intersection? Well, the symbol is A with an upside down U, B. And this is the AND operator, and it looks like an AND operator that's been softened. It's X such that X is an element of A and X is an element of B. So before we go further, just understand that if you wanted to analyze what it means for X to not be in A union B, you would negate what it means for X to be in A union B. We don't negate the domain. The domain is, some universal set that we haven't specified. But we would negate using De Morgan's laws an OR statement to get an AND statement with X not an element of A and X not an element of B if we wanted to analyze what it means for X to not be in A union B. And there was also the set difference, same with the intersection, of course. I won't go through that and bore you, but I think you can see what I'm saying. We just negate our definitions if we want to know what it means for X to not be in one of these sets. Do you remember what A minus B is? It's X such that X is in A and X is not in B. And so our algorithm to find A minus B was start with elements that are in A and then literally subtract away any of those that are in B to be left with elements that are in A but not in B. We have a couple of new definitions, so we need to discuss the concept of this universal set that I haven't really made apparent. So the universe, or the universal set, is denoted by a U with ears, and in some sense, it's the biggest set around. I'll put that in quotes because that's not very technical, but it's a set that contains all the elements that are in play. And there are usually several reasonable choices for a universal set. It's not unique. You have to be told or you have to be given a default. universal set. So there are usually several reasonable choices for a universal set. And what that is, it's any set that contains every element that's in play in a particular problem. Maybe I'll put a period here and make this a capital letter because I think this sentence is going to read better if I say any set that contains every element in play in a particular problem can serve as the universal set for that particular problem. And just FYI, folks, especially if the sets are real intervals of the line, or intervals of the real line, the default universe is always understood to be the reals. Unless we're told otherwise, that's the default. But a simple way to build a universal set is simply take the union of all of the sets that are involved in a problem. That will always work as a universal set. It'll be the biggest set around, and of course, by definition, the union of all those sets will contain every element that's involved in the problem. So armed with these ideas about a universal set, now we can have two new definitions: set complement and that's denoted with a superscript C. So we read this A complement. Well, what is A complement? It's the set of X in the universe such that X is not in A. So basically everything in the universe except the elements in A constitute the set A complement. And I know we talked about the cross product, but we will discuss that now again briefly. The cross product set, if we have two sets A and B, we're back to using two sets now because it's a binary set operator. This is called a unary set operator because it only gets applied to one set, is a set of ordered pairs. Parentheses, little a, comma, little b, close parentheses, such that this first coordinate, little a, is an element of set big A, and the second coordinate, little b, is an element of the second set, big B. So, you've played games with ordered pairs. Anytime you ever graphed a point x comma y on the xy coordinate, Cartesian coordinate plane, you were playing with the reals, cross the reals. So meta symbols are important, folks. You may not use set brackets around ordered pair coordinates. That wouldn't be an ordered pair. It would be a set. In a set, the order of the elements doesn't matter. In an ordered pair, the order of the coordinates matters. That's why it's called an ordered pair. So that's why we need to use parentheses rather than set brackets when we build ordered pairs. Symbols actually really matter. All right, let's start with an example here. And since we're back starting with a new section, we'll number our first example. Example 1, we want to practice these concepts. So in our example 1, we're going to give ourselves a finite example. Let's let the universe U be the set containing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have these 10 positive integers, the first 10 positive integers. And let's let A be the set containing 1, 2, 3, 4, and 5. let's let B be the set containing the evens, 2, 4, 6, 8, and 10. And let's let C be the set containing 4, 5, and 6. Okay? So let's find each set. We'll practice each of these set operations. A, find A union B. No, excuse me, that's a union. I need to put that the other way around. A union B. B, we're going to find A intersect B. For part C, we're going to find A minus C. For part D, we're going to find B complement. And for part E, we're going to find C cross B minus C. We'll start with those. So what do you think is going to be in A union B? By the way, A union B is a set. So we need to encase the elements in set brackets. All right? So what's going to be in A union B? By definition, any element that it's in A or in B or in both. Anybody?
Would it be 1, 2, 3, 4, 5, 6, 8, 10?
That's exactly right. If we just start listing the elements of A, we have to throw in 1, 2, 3, 4, and 5. Then we move on to include any elements of B. Well, 2 and 4 have already been listed. It's not wrong to list them again. In fact, that's one of the reasons why repeated elements naturally arise, as a result of the algorithm that just says, hey, throw everything in there that's in A, then throw everything in there that's in B, but we'll skip the 2 and the 4 because we know redundancy doesn't really add any value. 6, 8, 10, nicely done. What about A intersect B? It's the AND operator, everything that's in A and in B.
2 and 4.
Yep. The only elements that appear in both A and B are the elements 2 and 4. All right, A minus C. So again, we start with the elements of A and toss out elements from C. So we can write it. It's the elements that are in set A. So set A has 1, 2, 3, 4, and 5 in it. Then we're going to literally subtract away the elements that are in C. So we're going to subtract away the elements 4, 5, and 6. Notice 6 isn't even an A to begin with. Doesn't matter. Just ignore it. You can't take some 6 away from this set because it wasn't in there to begin with. But we certainly don't add it into A minus C because we don't want anything from C to appear in A minus C. So what elements will be in A minus C, folks?
1, 2, and 3.
That's exactly right. 1, 2, and 3. Good. All right. Now B complement. Everything that's in the universe.
It's the odds from 1 to 10.
That's right. B complement would be everything that's, between 1 and 10, but not in B. And of course, that's the odds because B is the evens. So, if you want, you can just make a note. It is the universe minus B, right? And so that's the odds, the set containing the odds to be precise. And now finally, for this cross product problem, we're going to do a set difference first so that we can get our heads around what the elements are that are going to contribute first and second coordinates. So C is the set containing 4, 5, and 6. But we want to cross that with whatever B minus C is. So we need to figure out what's in B minus C. Anybody? What elements are going to be in B minus C?
2, 8, 10.
Yep. 2, 8, and 10. Does anybody have any questions on why this set is the set B minus C? And now we're going to build the set that contains all the ordered pairs where the first coordinate comes from the set C. So the first coordinates are 4, 5, or 6, and the second coordinates come from the set B minus C. So second coordinates are 2, 8, or 10. And this is an example where we don't have any elements that are shared, but it is possible that you could have an element that appeared both as a first and second coordinate if you had a shared element in the intersection of the two sets that constitute the cross product. So open your set brackets. It is a set. And again, these are ordered pairs, so we must use parentheses. And so I'm just going to be methodical. There are numerous ways to do this and not miss any elements, but I like to do it in a lexicographical manner. What am I talking about? I want to take the first element by size from the first set, use it as a first coordinate in as many ways as possible, exhaust it before I move on to using the next element, namely 5 as a first coordinate. So 4 as a first coordinate could be paired with 2 as a second coordinate. Everybody seeing what I'm doing here? Or 4 as a first coordinate could be paired with 8. You can also draw a tree diagram to see. 4 could be paired with 10. Does anybody see how many elements we're going to get all together?
9.
I'm sorry?
9.
Exactly, because we'll have 3 choices for first coordinate times literally 3 choices for second coordinates. So now we've exhausted any way we could make an ordered pair using 4. So 5, 2 could be and you don't have to write them in this order. You just have to write the coordinates in order. We know that sets don't care what order the elements appear in. But I just like to do it methodically so I don't miss any of these elements. And close up your set brackets. So I will even make a note here to remember to close your set brackets. So a couple of facts about ordered pairs, or a fact about ordered pairs. I mean, what does it mean for 2 ordered pairs to be equal? And that's the point. That's why we can't use curly brackets to enclose the coordinates of an ordered pair. Because if, for example, if we decided, oh, I'm going to be a rebel and I'm going to use curly brackets for this ordered pair of 4, 2, well, that would represent the set containing 4 and 2, and order doesn't matter. And we know that would equal the set containing 2 and 4. You know, order doesn't matter for a set, but it does matter for an ordered pair. So that's one of the reasons why we want to, understand that for 2 ordered pairs to be equal, it's all about first coordinates being compared and the second coordinates being compared. So A comma B is equal to C comma D if and only if the first coordinates are equal. So A is equal to C and the second coordinates are equal. And that's what equality means when the elements are ordered pairs. Couple more just to look at, and we don't even need to know what the sets are, in fact. These are, for any set U and subset A of a universe U. F, what is the universe union A? And G, what is the universe intersected with A? When A is actually a subset of U. And we will review what subset means here in a minute. But every element of A is an element of the universe. That's what we're thinking about. So if we're unioning together the universe, which has every single element in it already, with one of its subsets, what do we get? That's right, Ronnie. We get the whole universe because everything's already in the universe. And if an element is in the universe or in A, well, it's in the universe because the universe contains every element. Everybody with me? So what about the universe intersect A?
Is it A?
It is. It's A because A, presumably, is the smaller set. I just want to show you now a nice diagram called Venn diagrams. If you wanted just a picture to help you understand some of these set operations. And again, you're not going to be tested on this. But there is a thing called a Venn diagram. This is a two-set Venn diagram where we have A and B and a universal set U. And notice we've drawn it so that there is definitely a region of overlap between A and B because there might be elements that are in there. Now, these numbers don't represent elements in any of these regions. They just are the numbers to identify the four regions that get created when we draw a Venn diagram that has two subsets A and B, okay? So one of the Venn diagram games is to shade each region indicated, and I just want to show you what it looks like. So A union B, well, by definition, is anything that's in A or in B or in both. So if we shaded the region that is, indicated by A union B, it would be the region of this diagram that is consisting of, the part that's region 1 and the part that's region 2 and the part that's region 3. You would just shade, these three regions. Whereas, of course, A intersect B is just this cat's eye region 2 that represents the parts of the diagram that are shared by A and B. And that's what the intersection is. It's the set of shared elements. This is nice if you don't really intuit complement. A complement would be the regions outside of set A. So that would be regions 3 and 4. These regions that are outside include, this region 3 that is contained in B because that part of B is outside of A. And to do later, go ahead and try to shade A intersect B complement, so first figure out A intersect B, which we did here, and what would the complement shading look like? A minus B. And here's a fun one. This is called the symmetric difference of A and B. And it's got a pretty, well, nice diagram because it's symmetric. Okay, so you can do that later, just for fun. Now let's do a formal review of this idea of subset of, and let's introduce the notion of proper subset of, which is, they're very much related. The interesting thing is in our textbook, the author declines to talk about a formal notation for proper subset of, but I'm going to show you one that's used often by set theorists. So recall, given sets A and B, we say, well, A is a subset of B. And it's denoted by, it looks like a soft less than or equal to symbol. A, and then, like I said, like a soft less than or equal to symbol B. And in some sense, A is less than or equal to B if it's a subset of. If, well, in fact, X in A implies X is in B. In other words, i.e., every element of set A is also in set B. Everything that lives in A is also living in B as far as elements. Well, here's the new definition. A is a proper subset of B. And again, I want to emphasize that for some reason the author declines to show the notation, but it doesn't hurt you to see it, at least one notation. I think one of the reasons she doesn't is because depending upon the level of the book, authors use a different notation, but this one is sort of self-apparent. A subset, but not equal to B. So listen, the slash only goes through the equality part. It's like less than, but not equal to B. If, well, two things. One, A is a subset of B. You got to have that A is a subset of B. And the second part is what makes it proper. A is not equal to B. But if everything that's in A is already in B, the only way A is not equal to B could happen would be, for example, i.e., there is some element X that's in B, but X is not in A. So there's something that's sitting in B that's not in A. Because subset of B could include that they're actually equal to each other. Just like, X is less than or equal to X is true for real numbers because X is equal to X. So, every set is a subset of itself, but a set cannot be a proper subset of itself because the superset, that's what B is called here, has to have at least one element that the subset does not have in order for proper to come into play. So let's look at an example. Let's let A be the set containing 1, 2, 3, 4, and 5. It's just a little simple finite example. B be the set containing 1, 3, and 5. And C be the set containing 1, 4, and 5. And I have not specified a universe here because I'm not planning on looking at set complement, but let's just think about this for a minute. What would be a reasonable universe for this example?
1 through 5.
Yeah, we could take A as the universe if we wanted to. A would work. So our answer is that A would work. Or, you could take the universe that we played with before, the elements 1 through 10. It just depends upon, the game that you want to play. So here, true or false? One, A is a subset of B. I'm going to skip a line so we have a little bit of room. 2, B is a subset of A. 3, C is a subset of B. And 4, B is a proper subset of A. So is A a subset of B?
Yes.
Let's look at our definition of subset. A is a subset of B means if an element X is in A, then X has to be in B. So do you want to say that A is a subset of B? Is everything that's in A also in B?
No, it isn't. I got it flipped.
Okay, yeah, right. You got to switch. Okay, cool. So good. False. And what's a reason why A is not a subset of B? Can you give me an X that satisfies the negation? In other words, X is in A and X is not in B. What an element that makes it not true?
2.
Yep. 2 is an element of A, but 2 is not an element of B, right? Or you could say 4 is an element of A, but 4 is not an element of B. You don't need both of those. We learned when we learned counterexample games. We don't need, both of them. Now, is B a subset of A though?
True.
Yeah. That's definitely true because the statement, if X is an element of B, then X is an element of A, holds. It's an if-then definition. What about C is a subset of B? Is C a subset of B? Good. Ronnie says false, and that's certainly false because 4 is an element of C, but 4 is not an element of B. And I know we're running out of time, but let's just finish this, and I'm going to flash you with something that will help you later, and we'll pick it up on Wednesday. B is a proper subset of A. Why? Well, one, B is a subset of A, was established already. We did that, up here. And two, there is an element. A has at least one element. In fact, it's got a couple. It has 2 and 4 that are not in B. I don't know how it is, but we are not done, even though we should be done. So let me just show you this last page of notes. And this is review. We covered interval notation at the very beginning of the semester, but here's just a review. We use square brackets, and this is the universe is the reals, okay? We're talking about intervals of the real line. So square bracket A comma B square bracket means X could be A, it could be B, or it could be anything in between. So think about it as closed hole. We use square brackets. Whereas soft bracket A comma B soft bracket is the strict. A is strictly less than X, and X is strictly less than B. So X is in here in the middle, but it can't be A and it can't be B. And then you can have, sets that are closed on one side and open on the other. They're called clopin sets. Yeah, that's a thing. It could be either way, where you've got the less than or equal to in one spot and the less than in the other spot. Then there's A with a square bracket, comma, infinity. That's just all the elements X that are bigger than or equal to A, or, less than or equal to B, strictly bigger than A with the soft bracket. Here's strictly less than B. I've drawn a picture. That's the open hole at B, right? But everything that's less than. And then from negative infinity to positive infinity is the reals. Notice when we're using the infinity symbol or the negative infinity symbol, we never use square brackets because infinity is not a number, folks. It's an idea. It's an idea of going on forever. So here's a nice important do later that you really should do later before the next class, to write each of these sets using interval notation and union symbols if needed. For example, you're going to need union symbols for D. You're going to have to use a union symbol needed because you'll use two intervals connected by a union symbol if you want to get the complement of this set that's somewhere at, in the middle of the number line. And here's a set difference. And notice, these are all integers, but I wanted to show you that we're talking about real numbers, folks. We're not talking about integers. These are not just integers. So in this last example, I stuck pi in there just as a reminder that even though we tend to resort to integers, certainly real intervals contain lots and lots and lots of numbers that aren't integers. In fact, they contain a bunch of irrational numbers. These are continuous intervals. There's an infinite number of elements in these shaded regions, okay? All right. Thanks for being here. Thanks for playing. Any questions? Let's go back to the gallery. Okay. All right. Well, you've got good stuff to work on, and I will get that next special homework up no later than in the morning. And check out those office hours if you need help attacking special homework number 9. I'll stick around for a few minutes in case anybody wants to talk after class. I'll stop recording.